So, in today's lecture 23-24, we'll be talking about the solar resources, insolation on collecting surface, tracking system. Okay, and thereafter we will have the PV system modeling, electrical and material characteristics of the photovoltaic system. 25th and 26th. Then a combined slide for two sessions, 27 to 30. It is basically an overall photovoltaic system covering the different aspects of the grid connected and isolated PV system. Okay, so I believe that if you sincerely attend this session, you will be quite good expert, quite good knowledge about the photovoltaic system. Okay, so you can check how much is your knowledge now. Okay, how much will be your knowledge at 5:30 p.m. in the evening. Okay, so you will find a lot difference. Okay, no one will be giving this statement like this. Okay, but as you see that university teaching is different than the school teaching, right? So I will just, mentoring you, I will just referring, I cannot go teaching line by line. Okay, so here, first of all, all the material, most of the material taken from this lecture is from the book GM Masters. Please note down, GM Master, title is Renewable and Efficient Electric Power System. I repeat again, GM Masters, Renewable and Efficient Electric Power System. It is IEEE Press, year, I think 2003. Okay, so please, you can Google it and you should be able to download it. Anyone want to download now? Please, you can download this book. Is very useful book. Okay. Even if you are teaching any renewable course, so this book you'll find, in my opinion, like among the best book. Okay. So from that 2003 version, and then it's one new version came in 2013. So some improvement, but not significant, not something drastic change. Okay. Steady state change. So still 2003 version holds quite good. Of course, some of the information data you can find little bit old, but still technical information doesn't change. Basic equations remain same. Okay. So from that perspective, this book is very good. So from that book, what I am going to cover, chapter 4 is solar resources. Chapter 5 is material and electrical characteristics, and chapter 6 is 6 or 7 is on the photovoltaic system. Okay, so here I am just going to start. Broadly, I will try to cover this material. Okay. As far as I can cover. Most of the important points I will try to touch upon. You will see that it will be more than what I am supposed to cover in my session. Okay. So here, this first session is talking about the solar resources. Okay. Like the input to the PV panels. Input to the PV panels, sun rays, at what angle you will be placing the PV panel. So all these resources you are going to learn from this chapter. Okay. So this chapter you will find very complicated mathematical equations. Okay. So neither you need not to memorize these equations, but you basically understand them. Okay. If you want to just online test, if you have to refer, you can just use them. You have some basic idea. Okay. You need not to memorize this. Okay. Even you try to memorize, you cannot, because equations are really very difficult. Okay, and you need not to feel unnecessary tense or pressurize that this is too complex. You have to just little bit understand and see that when you are watching movie, just relax and watch it. Okay, so but it is very interesting. You'll find this information really very interesting. If you have to calculate how much is the distance of Earth to Sun, so you'll have formula you can calculate. Okay, so the chapter is really very interesting. Okay, so here what we are going to cover: solar radiation, Earth's orbit, altitude, angle, different angles we are going to talk. Altitude angle, declination angle, solar position at any time of the day, sun path diagram for shading analysis, and then how much insolation is falling on the PV panel. Okay, so three parts are there. One is the direct beam radiation, and then you have the diffuse radiation and reflected radiation. Okay, so mostly it is direct, around 85%, then 10% say coming from the diffuse, 5% coming from the say reflected. I'm giving the approximate value. Okay, so these 10%, 5%, these are also very important. So we are going to see and understand that as well. And then finally, we talk about the tracking system. Okay, so this is what we are going to cover. So as I mentioned yesterday as well, this statement, most of the material coming directly from the book I mentioned. Okay, so here, as I mentioned yesterday, Earth received power from the sun, Earth surface 1.2 into 10 raised to power 8 gigawatt. If you can just tap this whole power from the sun for 1 hour, it will be sufficient for the whole world for 1 year. Okay, so you can see that how much is the potential from the sun. Okay, I try to relate it little bit spiritually. Okay, like you see, like all these Hindu people will know that we call it like 5 tattvas: Jal, Prithvi, Agni, Vayu, Akash, right? So what we have exploited mainly like Earth, taking coal out from the Earth, generating electricity from water, like that. Okay, so but we have not exploited the other tattvas like air and the energy from sun, right? So energy from sun, okay, solar, or the energy from air, wind. Okay, so these are naturally very clean and sustainable. I'm trying to present little bit different way. Okay, I just want to tell you what is there in the book. What is little bit my thought, how I'm going to relate it. Okay, so basically now it is a time to exploit out of these 5 tattvas, like we had coal, unnecessarily, extracting too much. Okay, for example, we have cow, we are taking the milk, that is good, but not killing. So basically what I'm trying to say that Earth, if whatever useful we can do, but not damaging. Okay, so this is very important. So like Earth, same way, water, not polluting water. If we pollute, then it will have bad effect ultimately on us. Okay, so whatever we have exploited, mainly that, and lot of pollution. Now basically, in a balanced way, all these 5 tattvas, like we try to have, something in a balanced way. So now it is a time to have more from the solar and wind. So here you will see, interestingly, the other forms of the energy like wind, hydro. I'm not expert in the area, but I am just trying to cope up. So you'll agree that whatever we study in the physics or science, wind, hydro, wave power, etc., directly or indirectly depend upon the sun. Okay. So, and you have seen that this, of course, we talked in the first lecture as well. So, how convenient it is to generate the electricity. It is most convenient form of generation of electricity. Do you agree or not? Okay. It is the most convenient. How much convenient? Like as you go in the market for buying of vegetable, right? If you see some person selling PV panel, you have PV panel instead of vegetable, just install it. In half an hour, electricity will start generating. Am I right or not? So it is the most convenient and simple way of generation. So and so many advantages it has. No noise at all. Completely environment friendly. I showed you the picture first day. How much pollution it will be there? Almost no pollution. Fuel cost is free. No fuel cost. Okay. Overall cost, previously it used to be costly, but now cost is no more an issue. Okay. So all these positive points are there. The only one issue little bit we have, that in the night no sunshine, and during the day little bit weather is not good, then no power generation. But otherwise it is generating power which is clean. Little bit issue of the low efficiency, but hopefully efficiency will improve further, and as we are not using fuel, so it is not that a big concern. Okay. So now basically you'll see that when we are designing a photovoltaic system, so design of PV system where you are going to install, it is basically a particular place, particular location. How much, like the weather, how is the weather? So different places, weather will be different. What you have weather here, weather in Srinagar will be different, weather in Tamil Nadu will be different. Okay. So the design of PV system relies on careful assessment of solar radiation at a particular site. Okay. So sun will emit as an average of energy flux of 1377 watt per meter square just outside the Earth's surface. So the total, please try to understand little bit some of the technical terms. Total power falling from the sun on the unit area is called as the irradiance. So some of the names, like we call it irradiance, radiance, sun rays, all these terms similar. Okay. So when solar radiation enters our surface, a part of the energy, like when the solar radiation will enter in the Earth surface to inside reaching the Earth. So as you see in the atmosphere, we have the dust. Okay. So we'll not get the whole sunshine. Okay. Part of that will be absorbed by the air molecules. So here we are going to see again the three important points I told you, how the sunshine will be finally falling on the PV panels. Okay. So here you can see that in the figure that the radiation which reaches the surface directly is called as the beam or direct radiation. Okay, some of the technical term please try to understand. So whatever this, the radiation reaching directly on the surface, earth surface, we call as the beam. Okay, some of the radiation may reach to the surface reflected from the ground. So these some of the rays reaches on the ground and then say reflected on the PV system called as the albedo. The total radiation consisting of these elements is called as the global. I'll explain this again. Again, this will come at later part. Okay. So now here, the amount of radiation which reaches the ground is widely variable because of the daily and yearly variation due to the motion of sun, irregular variation caused by the climatic condition, cloud, etc. So you will not have the consistent radiation throughout the year. Okay, it is obvious. So for this reason, the design of PV system refers on the input measured data close to the site. Okay, you need to have this some data information. Okay, so another one technical term which is used, a concept which characterizes the effect of clear atmosphere on sunlight is called as the air mass ratio. So whenever you are doing calculation, one term will come AM. AM stands for the air mass ratio. Okay. So here, what is this air mass ratio? You can see this figure as well. So here, on a clear day at sea level, the radiation from the sun at zenith, just like say, perpendicular, it is 1 air mass ratio. Okay. So as an average, how much ratio is considered as an average in calculation? So air mass ratio of 1.5 is assumed as the air mass ratio at the earth surface. Okay. So here you can see H1. Here H1 is the path length through the atmosphere with the sun, perpendicular. Okay. Directly overhead. H2 is the path length through the atmosphere to reach on the surface. You can see H1 and H2. From this, you can find this angle beta. Okay. So this beta is your H2 by H1, which will be 1 by sine beta. Okay. So this is what we call as the air mass ratio. I will not go into too much of these details, but once I little bit explain, you can understand it very well. Okay. Now, and honestly telling, I am not expert in this area. I am just giving you very general idea. Okay. Once I tell you, you want to build up, you can build up upon that. Okay. So here, as you know, the Earth orbit, how the Earth moves around the sun, how much is the Earth distance. So you'll find very interesting information. So how much is we would have studied long back in physics, but we do not recall every time. Do you agree? Okay. So here you will see that at different different days of the year, so distance is different. Okay. So for example, when we have this winter solstice, 21st December, the distance of Earth from Sun is 147 million kilometers. When we have this summer solstice, June 21st. This distance is 152 millions kilometer. Okay. Then on the vernal equinox, March 21st, and here it is autumnal equinox, September 21st. Okay. So here the tilt of the Earth surface, the tilt of the Earth's spin axis with respect to the ecliptic plane is what causes the season. As you know that how we have the different season, so it is because of that. So Earth moves round the sun Earth moves out the sun in an elliptical orbit, making one revolution in around 365 days. Okay. So here this formula very interesting. Okay. So using this formula, D is equal to 1.5 into 10 raised to power 8, 1 plus 0.017, 360 in bracket n minus 93 divided by 365. Okay. Here you need not to worry at this stage from where this formula came, how you are going to derive that. Okay. You need not to go into too much of deeper to know each and every formula unless you are doing PhD around this topic, right? So you are the application user. So using this formula, here you'll see in this equation only variable quantity is, and this formula is very simple. Here n is simply number of days. Okay. If we have today, like say for example, say 10th January, so n will be simply 10. If you have 10 March, what will be n? January 31, February 28 or 29, and January 10. So using n is very simple. You substitute the value of n, you will be able to get the distance of the Earth to Sun. Did you know this formula? Okay. So you will be like the Jyotsi. You know the Jyotsi? Do you know Jyotsi? So you can tell, okay, today how much is the distance? Distance of the Sun from Earth. Interesting or not interesting? Yes? Please say yes or no. Yes? Okay, so that's why I told this thing going to be very, very interesting. Right? So then another angle, what you see here, this angle, what you see here, angle delta. So this angle is called the declination angle delta. Okay. So here, as we know, as you study, Earth moves around the Sun. Okay. That is what we study in science. Okay. Now here, assuming that, one is stationary, one is rotating, you can consider that, say, Earth is stationary and Sun is doing movement. Okay. Just for your reference that it becomes easy to analyze. In science, we can assume anything, no harm in that. Right? So you'll see that on the different days, like say June 21st and this June, December 22nd. So this angle delta, declination angle delta, it has maximum value which is 23.45. Okay. Why all this angle we are doing? At the angle, at the end, what you are going to see, how much angle you are going to place your PV panel. Okay, all this complicated thing, why you are trying to learn so many angles? Story is simple, that at what angle you are going to place the PV panel. Okay, so the angle formed between the plane of equator and a line drawn from the center of the sun to the center of earth is called as the solar declination angle delta. How you can calculate this angle delta given by this formula. This delta is equal to, this chapter is 7 from that book I asked you to download. In that book, it is, this angle is given here, and in this variable quantities again n is same what I told you. So you can easily calculate, and this maximum value of this angle delta will be 23.45. It will be June 21st and December 21st. Okay, so you can do this as well. Then there comes another angle, altitude angle beta n. Okay, so here I am not going into too much of detail, otherwise your and my battery will be unnecessarily exhausted. Okay, so here you can see same way there is angle called as this beta n. We are aware of this, what we call as the latitude. We are not going into unnecessarily too much of details of doing these calculations. So you can see here that altitude angle beta given by this equation 90 minus L plus delta. L is the latitude and delta is the declination angle. Okay, and then from here you can find tilt angle. So at what angle you are going to place the PV panel? So tilt angle will be 90 minus beta n. Okay, now what is the greatness of this book I mentioned? You can find so many books, okay, on renewable energy. So here the great part of that book is that it contains lot of solved and unsolved problems. Okay, it contains each chapter 10-15 solved, 10-15 unsolved problems. So you can have sufficient practice. So I will not go because of the time constraint, but I encourage you as per your convenience. If you are interested knowing this PV system quite in detail, if a lecturer you have to teach, so this is in my opinion very good material. Okay, and the example created are not just arbitrary that you have any value, just make the example. So this you will find it quite practical. Okay, this book written by the US author, as you know, northern hemisphere, southern hemisphere. Okay, so that difference you have to just keep in mind. Everyone aware of the northern hemisphere, southern hemisphere, right? So how things changes, so you have to be mindful about that. Okay, so another interesting point, you can see that if you want to know the position of the sun at any time of the day, you want to track the position of the sun at any time of the day. So what you need to know? You need to know the altitude angle beta, and then there is another angle, azimuth angle of the sun called as the phi s. Okay, so this value of the beta and phi s will depend upon the another angles called the latitude, the day number and time of the day. Okay, so this azimuth angle phi s, the convention, what is the convention? That this angle will be positive in the morning when sun is in the east, and this angle will be negative in the evening when sun is in the west. So now you can do the calculations using these two equations, sine beta, then sine phi s. So all these angles you can do the calculation. Then there is another angle called as the hour angle h. So here this angle is that, as we know, that earth rotates 360 degree in 24 hours. Okay, so 360 divided by 24 rotation per hour. How much? 360 divided by 24, 15 degree. Okay, so in 1 hour rotation is 15. 3 hours 45. Okay, so this is called as the hour angle. Okay, accordingly, if you have at 11 a.m. solar time H15, okay, so earth needs to rotate 1 more hour. Okay, at 2 p.m. considering midday, so 2 p.m. is 2 hours, and after 12 it is minus. Okay, before 12 a.m. positive, p.m. negative. Okay, this is our angle. Okay, so all these numericals are given. I'm not going into that detail, but it is self-explanatory. All these calculations you can easily do that. Then another interesting point in PV system design, you are going to consider about the sun path diagram because of the shading analysis. So as we know that the shading is a problem for the PV system. We have to avoid the shading. If you have any tall building, trees, so you have to be careful, you have to be mindful that shading does not occur on the PV panel. Okay, you have to have some prediction where you are going to install PV. See, any big hotel is not going to come, which will cause the shading. Okay, so all these things you have to keep in mind. So this way we will have the shading analysis, shading diagram throughout the year. Okay, and then wherever we have our office or wherever we are going to have our PV system mounted, and then we are going to see nearby big trees or some tall buildings are going to come, and then you just see that any time of the day throughout the year that shading does not occur on the PV system. Okay, so this is the meaning of the sun path diagram. Okay, particularly when you are planning for, say, some big system. Okay, even for the small system, it is very important to have this understanding of that. Okay, so is it clear, please? Excellent. Now basically this slide, as I explained, the beam, albedo, global. So here it is very clearly explained in this slide. Okay, so here you will see that this is your collector, means PV panel. Collector means PV panel. From sun, like you have this, like the direct rays coming on the collector. So it writes this I stand for insolation level. Okay, I was teaching this course someplace, they were not expert, so I said insolation. Then someone said, is it insulation? I said, no, it is not insulation. Insulation is different. It is insolation. So we have to pronounce correctly. Okay. So that people don't get confused. Okay. So it is insolation, not insulation. Clear? So here I is the insulation, B stand for beam, direct. Okay. C stand for collector. Collector means PV panel, which collects the sun rays. Okay. So this is the IBC, clear for everyone? So direct beam coming on the PV panel, IBC. Then you will see that sun rays will be falling on this nearby area, could be floor, any glass window. From there, it will be reflected on this PV panel. Sometime when you are sitting in the room, you will see sunrise, sun is rays coming inside the room, then see from where it is getting reflected. Okay. So this term same way, IRC. So here IB, I is the insolation, R stand for reflected. C is again for the collector. Here the sun rays going into the clouds. From the cloud it could be diffused, indirect. So this is called as the IDC. Okay. Most of the insolation is be direct 85%, but then around 15% coming from both diffuse and reflected. So when you are dealing the analysis, having the knowledge of this is very important. Okay. So here basically you see that now whatever we talk that on the Earth surface we have this solar constant, how much insolation is there on the Earth surface, 1377, right? So then we are going to see how much we are able to receive on the PV panel. Okay. So again some sort of calculations we are going to do that. You will find some little bit complicated equations, but once you practice and once you get an idea, then it's not that difficult as well. Okay. So here basically I say that starting point for clear sky radiation calculation, I naught from sun passes perpendicularly through the imaginary surface outside the Earth surface. I naught can be written as SC. SC is the solar constant, which is 1377 watt per meter square. N is the day number, so you can find I naught. This I naught you can find. Okay. Then how much is the beam? So beam you can calculate from this relation, IB is equal to A into e raised to power minus km, where IB is the beam portion of the radiation that reaches the Earth's surface. A is the apparent extraterrestrial flux. K is the optical length. M is the air mass ratio. M or AM is the air mass ratio. So using these two equations, as I told you, this chapter full of formulas, full of equations. You need not to memorize. If needed, you have to just use. Okay. At the end, I am going to tell you, even you can have your small Excel program. You can feed all these in Excel program, and then within few minutes you give input and you can get the final insolation at a place. Okay. As simple as that. Okay. So A is given by this relation. Interestingly, you will find that all these depends upon n. N is the day number. So you have the value of A, you have the value of K. So A, K, air mass ratio is N. So this way you can find the I, B. Okay. Then, you know, optical depth K, either you can use those relations, those formulas I told you in previous slide, or you can have some data for a particular place, and from there you will have this table. You can know from this table the value of A, C and K. So depending upon this, like the day or month, you can get these values. Okay, and you can also use the formula. So both will come very close. Both will come very close. So this example, try to explain same story. Okay, so you can find the value of A and K using the formula, and you can also use the table. So the value will come very close. I'm going fine or fast? Okay, because I'm teaching more than the university students, PhD faculty, more than that. Okay, so I am just mentoring. I'm not teaching line by line, correct? Okay. Now, solar insolation on a collecting surface. At the end, you want to know how much insolation is coming on the PV panel. So here, it is reasonable accurate to calculate the clear sky direct beam insulation. Direct beam insulation you can calculate quite accurately, but it is very difficult to exactly calculate the diffuse and reflected. But if it is little bit approximate, that's also fine. Okay, so it is basically kind of a bonus. Okay, bonus you cannot exactly calculate. Salary you can exactly calculate. How much you will get bonus, it will decide by the government. Even you cannot calculate exactly how much will be your DA. It depends upon government, sometime 2%, sometime 4%. There is no formula that you will know. Can you predict? Difficult, right? You cannot calculate bonus, you cannot calculate DA. So what beam you can calculate, you cannot calculate very correctly diffuse or reflection, but it is a bonus. So how much more you can get it is good, right? But it is very important to know about that. Okay, bonus is 1 month salary. In some public sector, it could be 2 months salary, which is good saving, right? So you cannot neglect that, right? Very important. Mostly saving from there. I'm just trying to make the things not very boring. That's why I little bit introduce. So here you'll see that the diffuse radiation is assumed to be coming from all direction. So angle does not matter. Diffuse comes from all directions. So angle doesn't matter. Its value could be typically from 6 to 14%. Here, whatever is written in the textbook, it is exactly coming from as it is. Okay, so no addition, no correction from my side. Okay, then reflected is basically surface in front of PV panel. Okay, how shiny is the surface? Accordingly, you will have reflection. It will be changing. So this surface reflectance rho, depending upon the surface shining, the value could be 0.8 higher side, and lower side it could be 0.1. So this reflectance will be depend upon the surface. Now we talked about the IB beam. So beam may not fall a perpendicular to that. Then we will be beam is the then we will be interested that beam falling on the collector. Okay, so I have to see this term little bit carefully. So IBC is the beam falling on the collector. So it is given by IB into cos theta. I'm not going into these equations too much in detail. Then again, whatever the cos theta, it is explained. It also depends upon several other angles. So given by this equation 7.26. And then all these calculations you have to find for IBC, making use of all these formulas, you can do. You'll be able to do it. If you are required to do, you can self-study. Yes or no? Agree? Okay. So that's why if I had dedicated 5 days only solar, I would have done most of the problem. But here, half day difficult. Okay. And no need. Okay. If it is bachelor class, bachelor photovoltaic, I would have done that. But for more than PhD, very difficult. Okay. So diffuse radiation, diffuse just coming from the dust and then diffuse from there. So diffuse radiation on the collector is difficult to estimate accurately. Incoming radiation can be scattered from atmosphere particles and moisture and can be reflected by the clouds. Some is reflected to the surface, re-reflected. Okay. Reflected, re-reflected. So how much accurately you will calculate? So difficult. Exactly. So basically, how you are going to make an estimate about this diffuse. So IDH, I stand for insolation, D stand for diffuse, H stand for the horizontal surface. So that will be C into IB. IB is the beam, C is the sky diffuse factor. So these monthly values of C also in this next table are given there. You can calculate, you can also calculate from the table, or you can also calculate the value of C from this equation 7.28, and then that value of C you substitute and you can get this I diffuse on the horizontal surface. Then please keep in mind that this diffuse is going on the horizontal surface. From that diffuse you have to see how much will be the diffuse on the collector surface. So from whatever you had on the horizontal surface, like the diffuse coming from all the directions, you can see the diffuse. So this will be IDC will be IDH 1 plus cos sigma. This 1 plus cos sigma by 2, or CIB, this IDH is CIB 1 plus cos sigma by 2. So this is how you calculate the diffuse on the collector. The calculations are given. So that's the great part of the book, that any formula, anything you are doing, you can do the calculations, you can do some calculation, you can have confidence that whatever you understood is correct and you are understanding. Okay. Then talking about the reflected, this reflection can provide a considerable boost in performance, as for example on the bright day in front of snow or water in front of collector. It can be modest. For example, if you have some glasses nearby collector, so this reflection can be improved. Okay, so reflected radiation, the amount of reflected reflections can be modeled as a product of the total horizontal radiation IBH plus diffuse times the ground reflectance. So here reflected IRC you can calculate using this equation 7.30. Now whatever you have done, you see how much complicated formulas you have seen. If all the formulas you allow to come in your mind will become very hot, right? Do you agree or not? Yeah? Then you need tea, coffee, or like that. Okay. So whatever formulas you have got, you need not to allow to come in your mind, but you just make the Excel sheet. So please, the book I mentioned in the 2003 version. By the way, anyone download it? On and off student, anyone download it? Please download that and tell me that yes, I have done. At least one or two I really want. Okay. So in old version, this slide is not there. Okay. In new version, this is introduced. So all these you are seeing the different stuff on this part, like the some input you will be giving that which is needed in almost all the formulas, like the day number, latitude, collector surface, collector tilt angle, hour angle, all these input you are giving here. All this input information you are giving, you have developed your formula, you have placed this formula in the Excel sheet. Okay. Then after giving you input, you can calculate all this calculation, beam, IDC reflected, and then finally whatever you are seeing, my cursor please, insolation IC, you can calculate, it gives you value, for example, for this case 823. The three different part I explained you. IBC you are getting 697, IDC diffuse you get 88, IRC reflected you get 38. So total of 3 you get as the insolation level 823 watt per meter square. Okay. So whatever calculations I told you, for any place you have to do, for any place you have to do all these calculations. You will not have a textbook and you apply formula, the whole day will go. Okay. You make one small Excel program, just give the few input value, just in a 2 minute or 1 minute, you will get this. So is it easy or difficult? Easy, eh? So basically we application engineer, like download app, just put the input and get it, right? So but we as the engineer know that what is happening. Okay. Any application engineer, not necessarily to be an engineer. Anyone can do that. But engineer will know in the background what is happening. Other disciplined person will not know what is happening in the background. So this is the difference between the engineer and other person. Okay. So this is very good, and in the new book this has been explained. In the old version you will not find that. Okay. So we completed one part about this input condition. Now we are just going to talk the another part, what is the tracking system. You know that most of the place we have the fixed mounted panel. You decide the whatever these different calculations were there, you see at the end how much angle you are going to place it depending upon the latitude. Okay. Now you see that if some of the PV panels can we have the tracking system. Okay. As we know, if it is tracking, it can have more energy generated. Okay. But at the same time, you will see that when we are making this tracking arrangement, movement of the PV panel, so it will need the motor, it will need the device, sensors, it is going to add the cost as well. Okay. So here the tracking system could be single axis tracking or dual axis tracking. So here basically on some of the residential have fixed mount, but sometimes tracking system can be the cost effective. So tracking system could be single axis tracking or it could be two axis tracking system. For tracking single axis 20%, two axis 25 to 30%. Some of the companies who are making this tracking system, they will say, okay, please have this tracking system with us. Then you will obviously ask how much energy more I will get. They will say 50%, right? So you will know how much is the truth. So basically how much additional you can get. It says that 20% from this single and 25 to 30% from the two axis. Okay. Then again, you know, whatever these three calculation we did for the beam, diffuse and reflectance. Okay. When we are using the tracking system, there will be some change in the angles because you are tracking the sun position. Accordingly, whatever the equation you do, there will be some change, and because of that, it will deliver you more energy. So let us see that calculating the beam plus diffuse insolation on two axes is quite straightforward. The beam radiation on the collector is full insolation normal to the rays. Calculated using these equations, the diffuse and reflected are found using these equations. I am not going into the detail. Here in this new book, you can see that whatever the formula we used in the previous case without tracking, what formula we had, IBC was equal to IB into cos theta. Okay. So here when we are tracking, so this is the case for the two axis. If you are for the single axis, you will have the different equations. Okay. So how these equations for the two axes, how this equation will be modified, these are given here. So you can see that this is a two axis tracking system. Angular relations are given. Same way you can have this like the single axis tracking. So there are four different ways to do the single axis tracking. So this part is added in the new book. Okay, whatever you will see some pictures. So this picture, what I asked you to download in that book, you will not see that. Okay, so here you can see the single axis tracking. So there could be four possible options. Single axis tracking, how the PV panel can rotate. So you can see one is here horizontal north to south. Okay, you can have this horizontal east to west, or you can have this rotation about the vertical axis, rotation about the vertical axis, or you can have rotation about the polar axis. So single axis, you can have this for this different tracking system, and then accordingly you do some calculations to get how much insolation you can get it. Okay, so I'm not going into very much detail of that, but for one axis polar mount, one of the case, what will be the relations? So these will be the relations for calculation of the beam, diffuse and reflected insolation. And then this, in the new book, it gives you the relations for all the four cases. Okay, so this part is expanded in the new version of the book. Okay, now this example just try to explain you, like, you know, if you have single axis tracking system, you have the two axis tracking system, even you could have the fixed mounting, how much additional insolation level you can get using the tracking system. So I am not going into very much detail of that, but all this calculation you will find straightforward. In previous case, do you recall that the total insolation level what we had been getting in the previous case? If you recall that Excel sheet, if the value are same, so you can see how much is the total insolation, 823. You are seeing here that total insolation is 823 for the fixed mounting system. Okay, so if you use the one axis, if you use the tracking system, it gives you IBC 879. Okay, and then diffuse 115. Even the reflected it is neglected. So single axis, it is single. One axis, it gives you 994 watt per meter square. Sorry, that was the case for maybe two axis, and for the single axis you calculate for the beam and this diffuse. Even you can do the calculation for the reflected as well. Okay, so two axis it was 994, without axis it was 823, two axis 994, single axis 910. Okay, so you can see the difference, how much additional insolation level you can get with the tracking system. Okay, so this chapter talking about the solar resources. Okay, so here in this chapter what we have learned, you know, background about the earth rotation system, different angles. Okay, and then based on the different angles we know, we have the knowledge that how this insolation is falling. It is not only the beam, but it is the reflected or diffuse. Okay, how we do the calculation, then of course about the tracking. So this is the book I mentioned. It is same. The first version was 2003, then the original version 2003, 3 or 4, and this is the second. So it is published by GM Masters. Okay, 2013, it's very interesting to mention what you think that this professor, GM master, is from which discipline? Electrical, mechanical, civil? Which discipline? Is not electrical. Okay. Is I think from, you will check the cover or somewhere. So it is from the environmental or civil engineering. Okay. But has done the, in my opinion, great job, better than the electrical engineers. I have to be fair and honest from my perspective, right? Okay. Then this some of the material prepared by the another professor. So I am the user for that. I have not prepared all the PowerPoint myself. I have to acknowledge, I have to give the credit, right? As you are writing paper, everything is not written by you. Something contributed by others, so try to acknowledge everyone. Okay. Then, of course, we edited one book, Handbook of Renewable Energy Technology. So in that also one chapter was contributed by this Professor Keith on solar energy calculation. So this chapter gives you little bit additional information. So these are the reference. So I completed this chapter. I'm happy to take few questions. If you have, please, you have got any question, any comments from this chapter. At the end, you give the feedback. Okay. So feel free to tell how you like the chapter. Did your knowledge was enhanced? Yes or no? Did you saw some new terminology? Can you calculate the distance of Earth from the Sun with some formula? Yes or no? So it is great learning. Yes or no? So you can know the position of the Sun throughout the day. So this is great learning. Okay. 3 different ways of this insolation. So this chapter is like the very good knowledgeable. A lot of complicated formulas, but in practical implementation, not a problem. Just develop the small Excel program. When you can write the codes in Python, machine learning, so many high techs. So Excel is not very difficult. It will be difficult like for me, but not for the young guys. Okay, so any questions, any comments? Please ask anything you have. If no, then we quickly, in 2 minutes, we will have another just start. Maybe briefly how much we can cover, because we will have little bit time constraint. So I will briefly introduce. I think it is fine. I introduce and stop in between. Now we are starting this lecture 25 and 26. It is chapter 8 from the book I mentioned, GM Masters. So in the book, title is Electrical and Material Characteristic of the Photovoltaic Systems. If you have the book I mentioned, you can correct me. So it means I have read it little bit, yes. So we are going to speak. I will not go into too much of detail, but the main points I will explain. So again, you will find this whole material very interesting. So you can see how PV panel would look like. I'm sure that everyone have seen the PV panels. Okay, that is a different thing, that how closely you have seen, whether you have touched the PV panel or not. Power electronics guy would have touched it, or they have dealt with that. The people like me, I keep some safe distance. So what we are going to learn from this chapter. So what is this PV panel comprising of the cell? Okay. So what is the equivalent circuit of the cell? Then from the PV cell. We are going to build up the PV module, what we call the one PV panel module, and then after several modules we call it the arrays. Okay, so from cells to the module, module to the arrays. Then when we are saying that this PV panel has this much of power output, this much of efficiency, so we want to test the PV panel under the standard test conditions, in the field conditions. Okay, as we place the PV panel in the field condition, its performance, its power output significantly drops. Okay, so we are going to see how much is the drop in the power output in the actual field condition. Okay, and then we are going to see the shading impact on the IV characteristics of the PV system. So here, very quickly, I will just go on few points. Physics, you have studied what are the solar cell. So what is the solar cell in picture? You will see that, one small square box, you will see that it is one cell. Okay, so this way you can see in the panel you have the 36 or 72 cells. Okay, so cells are basically diodes. Okay, cells are basically diodes, and diode, as you know, is comprising of the PN material. From that simple knowledge, we know that this PV material comprising of the silicon or germanium and comprising of the semiconductor material. When these PV materials placed in the sun, so sunlight is converted into the electricity. And then some of these terms like the band gap for the silicon is of the order of 1.12 electron volts, means that electron needs to acquire that much of energy to jump into the conduction band. Okay, so a little bit you can see about the diode comprising of P and N type material. As you see, when it is in the forward bias, the diode current is there, but if you connect the diode in the reverse bias, current flow is just like the leakage current. Okay, so this is the symbol for the diode, and here this is the diode characteristic. So this part, diode characteristic in the forward direction, and this is the current, diode current, represented by this no load, means the current in the reverse direction. So current in the forward direction, you can see this is very important equations. You can please take a note of this equation. So ID is equal to I naught e raised to power 38.9 in bracket Vd minus 1. Okay, so from this you can write this equation in to find the diode current, and by rearranging you can also calculate the value of Vd, voltage across the diode. So both quantities ID and Vd you can calculate from this equation. ID you are calculating from this equation. How you will find Vd? Vd will be, first you say ID by I naught, then this term inside the bracket it has got the E term. Okay, how you are going to replace E? You take the natural log on both sides. So here it becomes natural log ID by I naught. Here these terms E just gets removed, it becomes 38.9 Vd minus 1, and then you divide by 38.9, and then 1 you take on the other side, you get the Vd. So it is very simple. Okay, so here these equations given, in fact original equation is Q Vd by Kt. When you substitute all these values, it gives you 38.9. Then you see that for the diode, you can do the calculation for this diode voltage. Even the current could be changing in the diode. For example, if you have the diode current, say 1 amps, how much voltage you get? 0.532. Okay. Even if the diode current increase significantly 10 amps, still the voltage you get is not much different. Okay. The voltage is higher, but not significantly, as you have current here significantly changed. Okay. So here the cell, as we say, is less like a comprising of the same semiconductor material. So you can say that you have got this one PV cell. So it is, you can just like the model, just like say a diode. Okay. So how you model? You have got a current source in parallel with the diode, and then you are connecting a load, and you can find how much is this current. You have got this current ISC, ideal source current ISC, then diode current and this current. Of course, any current you can apply at this junction KCL. Okay. So obviously ISC is equal to ID plus I. Okay. And this current ISC, this current is proportional to the sunlight or insolation. If insolation is more, this current will be more. If insolation drops by 50%, this current will drop to 50%. If there is no insolation, completely dark, so 0. Okay, it is proportional. Okay, so you can have this simple circuit model analysis. I am not going to the detail. It is same explanatory equation. I will be equal to ISC minus I naught, and the value of diode current you are placing from this equation. I already mentioned you. And if you substitute this I is equal to 0, I is equal to 0. I is equal to 0 means this is open circuit. Okay. So this open circuit voltage, if you substitute I is equal to 0, so you can calculate open circuit voltage. Okay. And then for any value of ISC, insolation level, we can calculate the relationship between this shell terminal voltage and current, what we call as the IV characteristics. IV characteristic of the cell or PV system. So this IV characteristic of the PV system is very important. Okay. Now you have this IV characteristics of the PV cell. Okay. So how we are getting? So basically, what does it says? That if you have this diode current, okay, this characteristics. So how you are going to see, like this curve, you just bring it down. And this current you just shift by your ISC. Okay. So what you are doing, first you bringing it just from up to the down, this curve. Okay. And then this part you just, because this is the current almost say dark. So if there is insolation level, whatever insolation level is there, you just make it up. So this is how you are getting this curve. Okay, this part you bring it from up to the down, and you just lifted this corresponding to IS. Is it clear for everyone? Okay. Now you will not have like one IV characteristic, but depending upon the change of the insolation level, this can become 50% here. If dark here, so you can have number of IV characteristics for the PV system. So it says that you can see that you can have the number of IV characteristics. So here you will see that even if this current is changing significantly, the change in this voltage, it will be very little. It will be very little. So again, the equations I mentioned you will be doing same way, and this equations relations mentioned here. You see that when you have IC is 4 amps, here IC is 2 amps, just insolation 50%. But you see that change in the even the insulation dropped 50%, but the value of the open circuit voltage, in one case it was 0.627, other case 0.61. So the open circuit voltage does not change significantly. Okay. Now this simple model, what we consider that cell with like the diode, it is not the like say very accurate representation or very realistic model, because thing is that, for example, we have got the cell. Okay, if cell will contribute the current, okay, any cell you have, the cell you place in your watch, obviously you connect in the circuit, it will cause the current. Okay, but when we are talking about the solar cell, insulation falling, proportional current will be proportional. If no current falling, means completely shaded, completely dark, zero current. Okay, so in principle it should be theoretically zero. That's the bad part of the shading, but the situation is not that problematic that it will be completely dark. So here it means that whatever model we considered, if one cell you make it dark, okay, then how much will be the current in the circuit? ISC, this is dark, the diode you connect in the opposite direction, so this current becomes almost zero. Okay, so that's the issue with what we call as the shading, but the situation is not as that problematic. Okay, so here when we are talking about the little bit more realistic model, so what we do, we consider there are several models proposed in the literature. Researchers are keep on working to develop more and more accurate model for this PV system. So here fairly accurate model you can consider that you have a small resistance RS in series and one parallel resistance, large parallel resistance in parallel. So in that case you can get a model for the cell, that a diode in parallel with a large resistance RP in parallel, and then of course you will add one series. But just to analyze the circuit, like just very step by step. Okay, first we consider only parallel resistance, then you want to find this current, simple circuit you can analyze. Okay, so all these slides very nicely explain this current I will be, this current I you can see will be ISC minus ID. This current will be VD, because in parallel voltage is VD divided by RP. So it is self-explanatory. Now in second case you consider, say if you have this resistance, this, then again you want to find the diode voltage. It will be your voltage V plus I RS. All these calculations you will see in the circuit, very simple. But when you are considering both RP and RS together, then you want to find how much is the current in the load, how much is the voltage across the load. So current, you can see this current I will be ISC minus ID divide minus this current. So this current will be VD divided by RP. This is the current in the circuit. How much will be this voltage V? So it will be whatever you have the voltage VD here or here minus I into RS voltage drop here. So this is very simplest circuit to analyze. Okay. So whatever you had the original IV characteristics, when you are considering this little bit more accurate model, so there will be little bit deviation in that curve. So you can see that because of the parallel resistance, the current will drop delta I, which is equal to V by RP in the parallel resistance, and there will be drop because of the series resistance. The drop delta V will be equal to I into RS. You can see the effect when this delta I drop is there. So whatever you have this curve, it will be little bit drop by this way. So the slope will be 1 by RP. And how you will consider the drop delta V, which is equal to IRS. So it will have this drop delta V is equal to IRS. Okay, so here we studied the basics of the diode. From the diode we compared that it is like a cell is just like the diode. We started with the very simple diode model, then we little bit modified, and we can see how these IV characteristics get modified. So you can see in this a PV panel, in the simple language PV panel, you see this one square, it is one cell. Okay, so here you see how much voltage generally it will contribute 0.5 volt. Okay, so this voltage is not any practical value, okay, for electricity generation. Okay, so obviously we have to connect number of cells in series and parallel to get the respectable voltage. 18, 36, whatever voltage you want to get. Accordingly, you have panels, number of cells are connected in series and parallel. So from this cell, you call it PV panel, or you have the module. Even this module has got the say power output say 150 watt, which is also not something significant. Again, you need the several panels even to meet the one house requirement. So you to get the required power, required voltage, required current, you connect this number of PV modules, panels in series and parallel, and then that forms from simple cell to the module, this module, and number of module, it makes the arrays. Okay, so you can see here cell to the module, and module to the array. So please give me little bit time, 10-15 minutes, so that I can complete this chapter, okay, rather than breaking and then restart it. So I'll please give me some time so that I can complete this. So you have, for example, a 36 cell. It could be like 36 cell, or it could be 72. So 36, each can have like say 0.5 volts. Theoretically, it should give you 18 volts, but there are resistance, etc. So typically you get the 12 volts. If it is 72 cell, it gives you voltage 24. Okay. Then all these simple equations, calculations shown here, resistance, all these calculations, you can do that. These are very simple and straightforward. So in fact, PV system, the calculations are really very simple. all these are like the DC circuit. The calculations are very simple and easy. Okay. Now here, for example, this spreads slide, very important, very interesting. From here, the concept of MPPT, maximum power point, it will start. Okay. So for example, whatever the voltage you saw, the diode voltage, say around 0.5 volt. Okay. Then you have this current from these equations. How much is the module depending upon the number of cells. Okay. How much is the power? Power is basically your current in the cell multiplied by the voltage. Okay. So if you little bit increase and decrease the voltage, say normal value is 0.5, you say 0.49, you do all these calculations. Then if you increase the VD little bit, 0.51, 0.52, etc. So, and then you get this current. Interestingly, current, all these calculations, based on the calculation, you do the current. Then you have this voltage and then power. So interestingly, you'll see that you'll find there is only one point where you will get the maximum power. Okay, only one point where you have get this maximum power. So that is called as the MPP point. So here, as you are doing this, like module, you are having the different number of modules you are connecting in series. Okay, so considering this simple circuit, say you are connecting 5, 10 or n number of modules in series. So this slide very nicely explains you. Maybe now or please later, as per your convenience, try to understand, try to practice. Okay, so then really you can have very well understanding. I'm not saying that just in 2 days, but whenever you have time, whenever you want, so you do a little bit practice, you really understand these things very nicely. Okay. Then same way, all these, what you had, that this IV characteristic for the N cell. If you had like one cell, it will like this. Okay. So depending upon how many cells are there, accordingly, it will have like these different curves. So finally, with the N cell, you have this current. You see in series circuit, current will be same. Okay. So whether you have one or N, current will be this. Okay. How the voltage will build up? 1, 2 up to N voltage build up on this axis. Okay. Then same way we are talking about the module with only parallel. Okay. How this effect is there? We are doing that modules with parallel only cell model. Like when we consider only this resistance, parallel resistance, how we are doing all these calculations. So simple and straightforward. I'm not just repeating, but when you have this parallel resistance, you show how this curve will drop. Okay, this is for one cell, and for N cell the curve is like that. So a generic model, that how we are representing the cell, a parallel resistance, then a series resistance across each. Okay. So if you are representing the model and then you are doing the calculation, do you find it difficult or easy? Fine. Okay. Do I need to explain more? No, I think, because this is very simple and you can learn very easily. Okay. Now basically here it will come the concept little bit, what you call as the fill factor and cell efficiency. You have got this IV characteristic of the PV panel. In this, how much maximum size of the rectangle you can fit in that. Okay, so here that will be your fill factor, and accordingly you can find the fill factor, this area divided by this total is like say your cell efficiency. So here basically when you have this PV panel, PV module, you want to test the PV system. Okay, so when you want to test the PV system, there will be some standard condition on which you want to test. So this standard condition is called the STC. So it is not a short course or like that, it is standard test condition, STC. So what are the standard test condition? We consider here insolation level of 1 kilowatt per meter square, air mass ratio of 1.5, and nominal temperature of 25 degree. This is the ambient temperature, atmosphere ambient temperature, not the cell temperature. Okay, so these are the standard test conditions. So when we have to compare the performance of the different PV modules from the different manufacturers, so we will test them under some standard test condition. Okay, now as we said that we expect that temperature should be around nominal one, but too much variations. Winter we can have 5 degree, 10 degree. Summer it can go nominal temperature around 50 degree. So how it affects the output power from the PV system? Common person will have thinking that if there is more, summer, it will produce more power, but it is not the case. Okay, so in hot locations, it is not the PV panel which will drop the efficiency. Even human being will drop the efficiency. Too much sweat, cannot focus for study. Right? Too much cold, difficult as well. Okay, we need ambient condition. Okay, so here basically with this, how the voltage and current affected, you see that the open circuit voltage will drop 0.37% per degree centigrade for crystalline silicon, while current increases by 0.05 per degree, and overall power decreases by 0.5% per degree. So these points for the crystalline is very important. You can have note down and maybe please you can use. Then cell temperature. First we talk about the ambient temperature. The cell temperature can be 25 to 30 degree above your ambient temperature. You have the ambient temperature, then cell temperature can be 25 to 30 degree higher. So in hot summer 35, here hot summer could be close to 50. Okay, so how much will be the cell output? So this cell temperature, how you will calculate the cell temperature? T ambient plus NOCT minus 20 divided by 0.8 into S. S is the solar constant. So this example explains you very well. I will quickly go through this example. So here you can see that impact of cell temperature on PV module. We have a PV module of 150 watt. Under conditions, one sun insolation, ambient temperature of 30 degree. The module has NOCT of 47 degree. Okay. Okay. From this, we find the cell temperature using this relation. Ambient temperature is given 30, NOCT is given 47, minus 20 divided by 0.8 into 1 sun insolation. So it gives you us the cell temperature of 64. So how the VOC and current will change, as it says that for module at standard temperature of 25, VOC for this table, for this module at standard temperature of 25, VOC is this. Since VOC will drop 0.37% per degree centigrade above 25, so this voltage from 42.8, it will drop. This is the equations. So 42.8 in bracket 1 minus 0.0037 in bracket 64 minus 25, it gives you voltage of this 36.7. And so your Pmax you get like your 150, what you had the nominal rating 150, so it will decrease by 1 minus 0.005, 64 minus 25, so the power output will drop from 150 to 121 just because of the one variation of the temperature. So you can clearly see the effect of temperature. एक टेम्परेचर की वेरी करने से 20% पावर रिड्यूस हो गई. Okay, now let us see the impact of shading. Okay, so as you see that when there is shading, it has significant effect. Power output could be dropped by 50%, even if a portion is shaded. Okay, so basically when you have the PV solar cell model you have seen, so when this cell is shaded, it means that it is not contributing any current. Okay, it means that becomes open circuit. So when you want to do the analysis, so here you can see that because of the shading, this is open circuit, and moreover you have many cells in series parallel. Say if one cell is shaded, okay, or few cells in the PV module are shaded, so you are going to analysis that obviously they do not contribute to the current. Whatever you have this current in circuit, the another bad issue what you have seen, this is not contributing, but this is causing the voltage drop because the parallel resistance is high. So if it is not contributing the current, okay, some person in the team, if someone is not contributing, it is okay to some extent, but if the person is causing the further disturbance, you will see how much is the problem. अगर एक आदमी काम नहीं कर रहा कोई बात नहीं, अगर टांग खिंचाई कर रहा है तो देखिए कितनी दिक्कत होगी. तो this is what it is happening here. It is having the not contributing plus causing the problem as well, voltage drop. So you can see this simple analysis. The additional points, the figure drawn are very simple, straightforward to analyze. So you can see that because of the shading of the cell, the voltage drop delta V, this amount you can get it given by this equation. We can see like when shading is there, what could be the solution, to avoid the shading problem. So one solution could be to provide the diode across each cell. So diode across each cell will not be very practical because it becomes very complicated. Voltage is dropped. So basically what it can be done, this is example. You can see that analysis of this circuit. What you see, how much the example we are continuing from 8.4 with some data. The voltage was 19.41. If one of the cell is shaded, even assuming that current remains the same, so what will be the new module output voltage and power? What would be the voltage across the shaded cell? How much power will be dissipated in the solar cell? So see, because of the shading of one cell, the voltage drop will be 14.66. Then how much will be the new voltage? New voltage will be 19.41 minus 14.66. So how much voltage you get? 4.75 instead of 19.41. There is significant voltage drop. How much power output you will get from the module? Assuming that current it is the same, current could also drop. So this module output will drop to 10.1. It was expected to deliver 41.5. It drops to 10. Just like the 25% you are getting, 75% is just gone because of the shading of one cell. Okay. In the same situation, if the student is done very wrong, okay, in principle lecturer should give the 0, but lecturer is little bit considerable, so at least give 1 or 2 marks or 25%. Even for the wrong, they will say at least something should be correct. Okay, so same story here, theoretically 0, but at least you are getting 25%. So this is really one of the big problem of the shading. So see how this shading can be avoided, shading diagram, all these things, shading, be considerable as far as possible. So all this calculation given here. And now we talked about that, if you connect the one diode across each cell, not practicable. What we can do, we can place one diode across each string. One series circuit, we can place one diode. The another issue sometime with the shading, what we see, that if you have got, say for example, some strings in the parallel, if one of the rows got shaded, okay, so current is being contributed by other rows, so whatever is shaded, they are not contributing. So what it can happen, that the current flowing in the load, the current can start flowing in this shaded portion, circulating current. So this can be another issue. So to avoid this problem, what it can be done, that for each string you place one diode in the reverse direction, so it will avoid the flow of current in the reverse direction. Okay, so this we completed. I thought that rather than breaking in between, we just continue. So this was the chapter 8 from the book I mentioned, electrical and material characteristics of the photovoltaic system. Here we show the model of the PV systems, starting from the basic concept of the diode. Then we moved to develop the realistic model using the RP and RS. Then we show the effect of the temperature, how the power drops, and then we saw the shading problem, how we can avoid the shading. So all these basic stuffs we have learned. So I just stop here. References more or less stay same, what we saw in previous chapter. So we are just going to stop for the lunch. And please, if you have any queries, question, you are more than welcome. If there are no questions, we'll stop about an hour. So please try to be little bit fast for the lunch, about 1 hour. And we can try to meet and try to complete according to the schedule. Thank you all for your kind cooperation. Thank you all.